Section 16.5, the nature of sound waves. So it turns out sound is a longitudinal wave and it comes from a vibrating object. So that could be a guitar string, that could be the human vocal cords, that could be the diaphragm of a speaker. But either way, we're going to have this transmission of the vibrations causing a wave to form. Now, in order for the sound wave to propagate, it needs to have a medium, right? So you can have sound exist in gas, like air, in liquid, underwater. Even sound can move through solids, but it cannot exist in a vacuum. That's why in outer space, there is no sound, because there's no medium to carry the sound, to really carry the disturbances, which is what this sound is. So to help us visualize sound, the longitudinal sound wave, we could go back to our slinky, right? And remember that we saw longitudinal waves with a slinky, of compressing the slinky or stretching it. It's the same thing with sound waves, where here we have a little speaker diaphragm, and as the speaker diaphragm moves outward, it compresses the air molecules right in front of it, right? The normal air pressure is fairly spread out, but there's what's known as a condensation when the speaker moves out. If the speaker then moves inward, the air molecules spread out, and that's known as a rarefaction, right? That's the opposite of condensation, and it becomes less dense, less pressure than the normal air pressure. So these slight changes in pressure are enough to be something that can transmit the sound from me to you. It's just very slight pressure differences. And if that's done regularly enough, right, then you can set up simple harmonic motion, right? You can set up a single sound that's happening, right? So if we notice these little red dots, this one dot is just going to move forward and back following simple harmonic motion, right? It's not, the dot itself isn't, this middle of the slinky isn't going to end up at the end. And similarly, the air molecules here aren't going to end up at the end. They're just going to oscillate back and forth. And we can look between condensations, from one condensation, one peak, to another peak condensation, and that will be equal to one wavelength of the sound wave. Right, so this red dot will just move parallel to the motion, and we can again measure that wavelength. Now, for what we hear, these different disturbances, it's not that one air molecule travels from the speaker to our ear, right? The individual air molecules aren't carried along with the wave, but they jostle each other. And so the jostling keeps getting passed along until the air next to our ear gets jostled and jostles our eardrum to be able to pick up that slight vibration, that slight disturbance that is the wave. So that's the basics of how a sound wave can travel. And this is why we need a medium like air, because if there's nothing to change pressure, if you're in a vacuum, then the sound won't go anywhere. Right? So some important ideas. One, with sound waves, we care a lot about frequency. So the frequency is the number of cycles per second. We've seen it before, but we say that a sound with a single frequency is called a pure tone. It just has one frequency going through it. It turns out many other sounds have one frequency you can primarily hear, and then they have a lot of other frequencies that are kind of built in to give it a particular sound. But a pure tone is just a single frequency going through. And the brain is able to interpret the frequency in terms of subjective quality called pitch, right? Pitch is how high or low something sounds, right? And this is something, I don't know if any of you remember a phone this old, but when you pushed the different numbers, you'd hear different sounds. And it turns out there's this pattern right? For each column, there's a particular frequency. For each row, there's another frequency. So anytime you push a button, two different frequencies sound at once. So that's why there's someone who has what's known as perfect pitch, and she could identify just by hearing what number someone had pushed on the phone because she knows the sound perfectly. So we could compare some of these frequencies, right? Like number pushing button 1 is 697 hertz and 1209 hertz. So there's this online tone generator. So 697 hertz, by the way, if you don't like tones, you may want to tune this part out. But hopefully it's not too loud. There we go. It's a little bit choppy. That's 697 hertz. Now we could add in 1336 hertz. So you can get a sense there. There's two different pitches, right? And the 1337 pitch sounded higher, right? It was a higher frequency. It was also a higher pitch. You can try that out with any number of different pitches, but I don't know how well it's going to record, so I think we'll leave it there. It turns out the human ear is capable of hearing from 20 hertz up to 20,000 hertz. Though, as you get older, the upper range drops, especially depending on how many loud concerts you went to. So, by your middle age, you can maybe hear 12 to 14,000 hertz, not all the way up to 20. And there's various uh, audio checks, right, that you can do a test of how high you can hear. So I'll leave that to you if you're curious to check how good your ears are on how much you can hear those higher frequencies. Right. And finally, you could also describe the pressure amplitude of a sound wave, right? If you had a tube that had pressure gauges above a sound wave that was passing through the tube, you'd see in the condensations, it's high pressure, and the rarefactions, it's really low pressure. So that could be plotted here, where the condensation, it turns out, will increase like a positive crest, and the rarefaction is like a trough. Right? And they're both slight changes from atmospheric pressure. It turns out the condensations and rarefactions, if it's just like a normal conversation, it's a difference of, let's see, 3 times 10 to the minus 2 pascals. That's really small, especially compared to atmospheric pressure, which is 1 times 10 to the positive 5th pascals. So it's not very big in the disturbance, but that's enough that we can hear it. And loudness is then an attribute of sound that depends on the pressure amplitude of the wave, right? If you increase the amplitude of the wave, then you are increasing what we hear as loudness, right? You have a larger pressure amplitude, larger differences in pressure. So this introduces the nature of sound waves. There's so much more you could study with sound, but this at least scratches the surface, and we'll see a little bit more with things in the next few sections, including the very next one, where we take a look at the speed of sound. So stick around.